So let's take a look at some very useful properties of definite integrals, which will help us in computing them. We're going to start with some definitions, and this might seem strange, okay, because usually you have theorems to prove the properties, but here we're going to start with some definitions. We're going to define switching or reversing the limits a and b of this definite integral with a minus sign. Okay, so if instead of integrating from a to b, you integrate from b to a, you can do so at the expense of a minus sign. Okay, so we have this equality. Basically, reversing the limits means you gotta include a minus sign there, so multiply by -1. Okay, this is a definition. All right, why do we need it to be a definition? Well, we talked about the definite integral being the net area. Didn't really have a sense of direction. Okay, but for our purposes, it's useful to have that definition, and it doesn't exactly cause any problems. It's harmless, so we will use this property that is given by definition, and there's a motivation for that. I mean, previously we've seen how delta x is equal to b minus a over n if you divide it into n subintervals. Well, if you flip that around, you get a minus b. Okay, so it's sort of flipping them. So there is a good reason to do it, but it's not a theorem. It's a definition. Okay, so it is useful, but it's a definition. The second thing, we'll define for identical limits, so integrating from a to a, we'll define this as 0, okay? Doesn't make sense otherwise, but to start and end at the same point, but we'll include this property as a definition. And although it's a definition, it is well motivated, okay? So if we're starting and ending at the same point, well, we're not going through any interval. So what's the net area if you're just stuck at one point? Well, there is no net area, right? So we'll define this to be 0 there, okay? In doing so allows us to now derive some interesting theorems. So let f and g be integrable functions on interval containing a, b, and p. And we don't make any statement on the ordering of these, whether a is larger than b or p. Okay? Just some interval, and that interval includes a, b, and p. Well, we could sort of distribute, if you will, the integral over a sum or subtraction. Okay, so instead of integrating the sum of f and g, you could integrate over f and then add the integral over g. Of course, both of these from a to b. They still have to have the same limits. We also have a constant multiple rule. So if you have a function multiplied by some constant, you could factor out that constant. And so instead of having it inside the integral, you could factor it outside of the integral. This works for any constant c. And we also have this property here, where the integral from a to b of f of x dx is equal to the integral from a to p plus p to b, okay? And this sort of has an intuitive meaning if p was a value between a and b, okay? So the net area, if you stop at some point p, but then continue back up to b, well, that kind of makes sense, but this even works if p is larger or smaller than a and b, and the reason it works is because of our definitions. Okay, that's why this would work. So this works for any p. And the reason why that property worked, you could see that when p is between a and b, well, the net area from a to b will be equal to the net area from a to p plus the net area from p to b. And so this is quite intuitive, and we could vary p, and it has an intuitive meaning there. But what if p was not between a and b? Well, again, thanks to the definitions that we used where reversing the limit introduces a minus sign, you could see that this relation still works. I mean, here P is to the right of B, and yet that formula still works. Okay? We could vary P and get it closer or farther away, but notice that you have the integral from a to p f of x dx, and you could see that the net area, well, you only want it between a and b. So what that formula there is telling you is if you want the area, the net area from a to b, you can integrate from a to p, okay? So go even farther than b, but subtract out that dark green area from the net area that you calculate, and it'll give you a to b. Now, why is there a plus sign? Well, what does that minus sign do to the limits of integration? It flips them. It reverses the limits. So our formula stands. Thus, we saw a visualization that hopefully clears that up. Okay. For this, the remaining properties, we'll assume the function f and g are integrable, but here we'll be strict about it, and we have that b is strictly greater than a, and we are considering integrable functions on the interval a to b. So the function absolute value of f is integrable on a and b, and the absolute value now is the sum of the areas of the regions bounded. Okay, so this, instead of giving you the net area, this gives you the actual area. Okay, so the area without, the signs. So it just adds up all of the regions, whether below or above the x-axis, all the same, and just adds the total area. So it's not net area, but actual area. If you want to know the area of the regions bounded by the graph of a function in the x-axis without the net area, just take the absolute value. And why that property works with the absolute value is you could see on the right here is the absolute value of the function on the left. Okay, so the function on the left is just f of x, and the function on the right is the absolute value of it. And so what it does is flips that r1 above the x-axis, and so you would end up getting the area, but not the net area. Another property of the definite integral is that if the function is greater than or equal to 0 on a and b, well, that means everything is above or on the x-axis, and so we would expect that the net area will also be greater than or equal to 0. If some function is greater than or equal to another function, so if f is greater than or equal to g on ab, then the net area, the definite integral of f from a to b, will be greater than or equal to the definite integral from a to b of g of x. And here, definite integral, net area, right, it's the same thing. And finally, if a function is bounded below by m and bounded above by capital M on ab, and by the way, we know that any continuous function on a closed and bounded interval will attain a minimum and maximum. Okay, that's the extreme value theorem. So if the function is bound, but we don't make that assumption. We just assume it. We're assuming that f is just integrable, right? It doesn't really have to be continuous, but if it was, then we know we have this. So in this case, the definite integral of f from a to b is bounded below by the lowest value that f would attain times the length of the entire interval, and bounded above by the highest value that f would attain on that interval times the length of that interval. And I hope that makes sense, as this is the area of a rectangle where the height of the rectangle is the highest that f could be, and this is the area of a rectangle where the height of the rectangle is the lowest that it could be. And here I say height, which could also include negative values, so m could be negative. We are dealing with definite integrals, so we're discussing the net areas. So let's take a look at this example in which we'll utilize the various properties we've discussed. So we're not going to get a function, but we are told that the definite integral of some function f, which again we're not getting, from 0 to 5 is 3, and the definite integral from 0 to 7 is minus 10. Okay, we want to evaluate the following integrals if possible. So here we have 0 to 7, 2 times f. Well, we're going to use the constant multiple rule and pull 2 out of the integral there, or factor it out, however you want to say that. And you so once you pull that out, you'll get just the integral from 0 to 7. Well, that's minus 10, and so we get minus 20. Well, what about the integral of f from 5 to 7? Well, we're going to take advantage of the property that we see here to write out, to integrate from 0 to 7, but we need to get rid of everything before 5, so we're going to subtract out 0 to 5 there. And so we'll get minus 10 minus 3, because this is 3 right there, and this is minus 10, and so you get minus 13. What about 5 to 0 of f of x? Well, we're going to take advantage of the definition of reversing the limits. It's minus, and now we get to switch the limits, and so net minus 3, so you get negative 3 there. So negative 1. This is basically a minus 1 there, times this, which is 3, so that's where that negative 3 is coming from. Here we're going to take advantage of the constant multiple rule, but we're not done yet. We're also going to reverse the sign. We've got to do 2 operations there. So you get minus 6 times whatever this is. What is that? It's minus 10. And so you get negative 6 times negative 10, and that's 60. And what about the absolute value of f from 0 to 7? Well, notice the integral, so the net area from 0 to 5 was 3. Then, as we went from 5 to 7, we got a minus 13 for the net area. But we don't know how that minus 13 came about. I mean, you could have had a situation where and even with the 0 to 5, we don't know exactly which aspects were above, which parts were above the x-axis and which parts were below, in order to flip those signs. So let me give you an example here. So if you have some function, and let's just say, okay, we're going to let that be 5 there and 7. Okay. Well, the net area that we would get from 0 to 5 will be 3. Okay, so the area of that, and then minus that part. And so that will give us 3. And then for this next part, we're going to want it to be a little more negative, right? So we'll have this going down here. Okay. And say there. Okay. Well, we don't know. So here we would have to flip this bottom part out, right? And this bottom part would get flipped above the x-axis once we take the absolute value. And so you could find the area of that and flip that around. But what if it wasn't that? What if it wasn't this function here at the end that would give us the values we have of our integral? What if instead it was, say, Okay, something like that there. Well, again, we would then flip this part out. But you could see that these wouldn't have the same area as that. I mean, they would still give you the same resulting value, okay? But since we don't know which parts are below the x-axis and which parts are above, then we can't make any general statement for the absolute value. So we'll conclude that we don't have enough knowledge for evaluating this last part. And of course, in the example that I had here, I didn't draw things to scale very clearly, right? But I was just trying to demonstrate that since you don't know which parts are above and below, in general, you wouldn't be able to compute the total area there from the net area, okay? But obviously, these are not drawn to scale.